So if we want to graph this line in a different way, we can do it. One other way we can do this, see, every single linear equation is going to cross both the x-axis and the y-axis, here and here. Or maybe it's going to be here and here. Or maybe it's going to be here and here. Or maybe it's going to be here and here. The only lines that don't cross both the x and y-axis are horizontal lines. They only cross the y-axis. And vertical lines that only cross the x-axis. Every other linear equation will cross both the x and y-axis. And when that happens, we will be able to find those points easily, and we can use them to graph the line, because we really just need 2 points to be able to graph a line. So if those 2 points are easy to find, being the x-axis, the x-intercept and the y-intercept, then we can use those. So we just talked about how to find the y-intercept without changing the equation, right? We know that on the y-axis, every point will have x equals 0. At the y-intercept, x will always equal 0. Now, if x equals 0, this 3x term is going to become 0, and it's kind of going to cancel itself out because 3 times 0 is 0. 0 plus 2y is just 2y. We could just solve this little equation, 2y equals 12, because that's all that's going to be left if x is equal to 0, is the equation with the y, not the x, because the x canceled out. And then if you divide by 2 to get y equals 6, there's the y-intercept. It's really 0, 6, but that's a point. See, we got that without isolating the y. We didn't put the equation in y equals mx plus b form. We only let x equals 0 to find the y-intercept. Now, we can do the same thing to find something called the x-intercept. The x-intercept will be a point on the x-axis. Now, if you think about all the points on the x-axis, they are up or down 0 units, which means the y is going to equal 0. If the y equals 0, then this y term is going to be 2 times 0, which is 0, and 3x plus 0 is just 3x. The y term cancels itself out when y is equal to 0, which leaves us with 3x equals 12, a simple equation that we can solve in one step to get the x-intercept is 4. Now, the x-intercept is 4 as an ordered pair is 4, 0. Don't put the 0 in the wrong spot. For the x-intercept, y is equal to 0. You have an x value, but y is equal to 0. For the y-intercept, you have x is equal to 0. You have a y value for the y-intercept, but x is equal to 0. So now, if we have the x-intercept is 4, we go over here to our graph, put a dot on 4 on the x-axis. There it is. And if the y-intercept is 6, then go up to 6. 1, 2, 3, 4, 5, 6 on the y-axis. There's 2 points. That's all we really need to graph this line. Now, the drawback is on this one is that I don't have the slope and I don't have all the other points to help me graph this line. So if I had a straight edge, it would be really nice. But I don't. So I'll just do the best I can to freehand that. And that's all I need to be able to graph that line. The x-intercept and the y-intercept. 2 points that are easy to find. To find the y-intercept, let x equals 0. To find the x-intercept, let y equal 0. Find those 2 points and graph the line. The only time you can't do that is if the x-intercept and the y-intercept are the same because the line goes through the origin. Okay. And when we have those special lines. Okay, so let's see what we have next. Special lines. Oh, look, we have special lines. Now, believe it or not, this y equals -3 is a line. And you're thinking, doesn't look like a line. All right, well, let's make an XY table and see what happens. Now, in our XY table, the only thing we know, usually we pick X values, right? So let's do that. 0, 1, 2, 3. Okay, but this equation says y equals -3. So it doesn't matter what x is, y is always going to be -3. So -3, -3, -3, -3. Notice that the y-intercept is -3. When the equation is y equals -3, the y-intercept is -3. So the y-intercept is -3. And those other points, 1, -3, 2, -3, 3, -3, they lined up on a horizontal line. So this one has a y-intercept, but no x-intercept. There is no x-intercept. Now, no x-intercept means it has to be parallel to the x-axis. And a horizontal line is parallel to the x-axis. Okay, now that should help you graph the next one. So the next line, x equals 4, this one's going to have an x-intercept of 4, which would be 1, 2, 3, 4 here. There's the x-intercept of 4. But on this one, every x value has to be 4. It doesn't tell us anything about how to find the y values. But if every x value has to be 4, then wouldn't it be something like this if we made a table? All the x values are 4. The y values can be anything we want. 4 is 0. There is our x-intercept, 4, 0. But then we also have 4, 1, 4, 2, 4, 3. All the x values have to be 4. So there is no y-intercept on this one. See, there's no y in the equation, so there's no y-intercept, because you can never solve for y. So if there's no y-intercept, it's got to be parallel to the y-axis. If it's parallel to the y-axis, it's a vertical line. So let's keep drawing that vertical line without hitting any more buttons on our iPad. And there we go. So there's two special lines. So if you have an equation with no x in it, only the y, like this one, there will be a y-intercept, but no x-intercept, which means if there is no x-intercept, it's parallel to the x-axis. It'll have a y-intercept, but no x-intercept. And if you have an equation with no y, but it has x in it, it'll have an x-intercept, but no y-intercept. So that'll help you figure out how to draw those special lines. Okay? So remember, the y equals a number that crosses the y-axis, but it never crosses the x-axis. The x equals a number crosses the x-axis, but not the y-axis. Okay. Now, we have to be able to use what we have just learned to solve some problems. This is, I know, your favorite part. But let's just take a look and see what we can figure out. So Mike the meteorologist launches a weather balloon from the top of a hill 500 feet above sea level. The balloon rises at a rate of 1,000 feet per minute. The balloon takes barometric readings every minute, but Mike has to report the altitude with each reading, make a chart and graph to show the altitude of the balloon every minute up to 30,000 feet. Write an equation to model the height of the balloon after X minutes. Okay, so let's write an equation. Let's do that first. Write an equation to model the height of the balloon. So whenever we write an equation to model the height of the balloon, then that kind of means that if we're going to use this form, since we're in linear equations, we're thinking, okay, this could be a linear equation, that y is going to represent the height of the balloon. And now it does say that x is going to represent the minutes. Okay, so if we use this form, y equals mx plus b, and x is the number of minutes, then the m, that's minutes there for the x, the m, which is the rate of change, remember, that's the slope, but it's also the rate of change in y over change in x, then what is the rate of change in this problem? Right here it says the rate of 1,000 feet per minute. So that's going to be our 1,000 feet per minute. Now look at this. The rate of change is in feet per minute. What is the x in? Minutes. If you multiply feet per minute as a fraction times minutes, what happens to those minutes? They cancel out and you end up with feet. Now the b is the beginning, right? Beginning, the y-intercept. No, the beginning on this one, where does it begin? He launches a weather balloon from the top of a hill that's 500 feet above sea level. So the beginning height is in feet. So if this all works out to be feet, that's the mx, then we can add that to feet and see now those are like terms. I can add feet to feet. Feet from the rate times the minutes and feet from the y-intercept. And that will be the height in feet, which is what we want. Okay, so how does that look when we're finished with our equation? So y, which is the height of the balloon at any x value, at any number of minutes, equals the rate m, so that's 1,000 feet per minute, times the number of minutes. So notice I did not put the units in for my final equation because they just kind of get in the way. But I want to use the units. See, I'm using the units here to figure out if I am correct. But when I write my final equation, I'm not writing them in there. So it's 1,000x plus my beginning height of 500 feet. So there's my equation. Now I want to graph that. Now on this one, I kind of want to be specific with my graph. I don't want to just kind of sketch something like this and go like that. I really want to use my equation to graph something with some precision. So make a nice graph like this. Okay, so there is our equation, y equals 1,000x plus 500. Now to graph this one, we have the beginning point, you know, the y-intercept right there. And 500 feet. This is altitude in thousands of feet. So this 2 right here is really 2,000 feet. Okay? So halfway up there would be 1,000 feet. 500 feet would be half of that, so it's a fourth of the way. Okay, so we have to estimate a little bit. So there's our 500 feet. Now, on this, it's really going to be hard for me, well, not too hard, to count for my slope, which is 1,000 over 1. It's going to be hard for me to count up 1,000 over 1. Okay, I mean, we could do it, but let's do this instead. See, on our input-output table, xy, we already know 0, 500. We have that point on our graph already. Okay, let's pick some other x value that we can use and do the math to find out what the y value is. Let's pick 10 for the x. Okay, so if x is 10, let's take 1,000 times 10, that would be 10,000, plus 500, and that would be 10,500. Okay, so 10,500 is going to be a little above 10,000. You know, 1/4 of the way between 10,000 and 12,000. All right, so let's pick another point, like 20. 20. So 20 times 1,000 would be 20,000 plus 500 would be 20,500. 20,500 would be just above 20,000 on our graph here. 1/4 of the way between 20,000 and 22,000. Hey, remember we were supposed to go up to 30,000 feet? What if x is 30? 30 times 1,000. I'm actually plugging my 30 in right here in case you were wondering like where are all these numbers coming from. 30 times 1,000 30,000 plus 500 would be 30,500. So let's go up here to find 30,500, which would be about right there. And there's our line. So I'm going to try my best to draw a nice straight line here. See what I can do to get that lined up. Like that. Okay, that's the best I can do with the equipment that I currently possess. All right, so there is our line. And we can show the altitude every minute, because the altitude every minute we can read from the graph. So in 1 minute, could be right there, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes. Well, I kind of missed. Okay, and that's what we needed to have. So now if we had a really accurate graph, then we could use that to like do all of our meteorological charting. Oh, very good. Let's try another one. As an event planner, Evelyn is arranging tables for a certain event. She has small tables which seat 4 people each, large tables which seat 6 people each, and she has to have enough tables to seat 180 people. Okay, what combination of small and large tables could she use? Okay, so this is not as obvious as the last one, because in the last one we had a beginning height and we had a rate. Nice. But in this one, we just have small tables and large tables. That's all we have. So let's choose variables to represent the things that are unknown. So we need some small tables. Let's let x represent the number of small tables. Number of small tables. Okay. And let's let y represent the number of large tables. Number of large tables. All right. Now, the only thing we know is that, well, we know how many seats are at each small table and how many seats are at each large table. We know that. And we also know that we have 180 people altogether. So let's write an equation that results in seating 180 people. So our equation is going to be all about how many seats are available. So each one of these small tables has 4 seats available, so that would be 4x. Each one of the large tables has 6 seats available, so that would be 6y. And that should be the total number of seats that are available, which we need to have 180 seats available for 180 people. So there's our equation, 4x plus 6y equals 180. Now in this case, right, one equation, 2 variables, infinite number of solutions, kind of. Number of tables probably can't be fractions or decimals or negative numbers. But we can use the equation to find those infinite number of solutions to help us find the ones that matter in this case. So we could either solve for y and use the slope and the y-intercept, or we could use the x-intercept and the y-intercept. If we use the x-intercept, the x-intercept, remember, is the x value when y is equal to 0. In this problem, if y is equal to 0, that means 0 large tables. If you have 0 large tables, how many small tables do you need to seat 180 people? Well, that would be 4x equals 180. Let's divide by 4 to find out what x is. 180 divided by 4. Oh, I should be able to do that in my head, but I'm not going to do it. 180 divided by 4, 45. So if I don't have any large tables, I need 45 small tables. Okay, let's find the y-intercept. Now the y-intercept is the y value when x is equal to 0. If x is equal to 0, that means we're going to use no small tables, all large tables. So our equation on this one would be 6y equals 180. Let's divide by 6 to get y equals 30. So if I wanted to use just large tables, then I would have 30 large tables. Remember that 30 is 0, 30, 0 small tables, 30 large tables. And this 45 is 45 small tables, 0 large tables. All right, so how can we use those numbers to find any combination of small and large tables she could use? Okay, well, let's take a look at a graph. So if we were going to graph that, remember we found the x-intercept was 45. The y-intercept was 30. So the y-intercept is 30 would be right here on the y-axis. Excellent. The x-intercept of 45 would be right between 44 and 46. Now I'm going to draw that line. My line is going to be really important in this case. I still don't have a straight line tool for this program, so I'm just going to line those up the best I can and draw a nice straight line, hopefully that will work. Okay, and then we can use that line to find our solutions. So remember, our solutions have to be whole numbers of solutions, and they should be on the line. So depending on the accuracy of my line, okay, keep that in mind, that these should be the solutions. I have a point right here. Well, first of all, let's make a table like this, x and y. Remember, x is the number of small tables. Y is the number of large tables. And I do have 0, 30. I have that. But I think this point is on that line, which would be 6 and 26. And I think this point is on that line also, which would be 12 and 22. Well, I'm finding a pattern. And I think this point would be on that line, which I think would be 18 and 18. Okay, look what's happening here. On my x side, when I find all these points, it looks like I'm going up by 6 every time. So I think the next one's going to be 24 and 30 and 6, 36, and 6 more would be 42. Okay, right here. And the y values, what are they doing? It looks like they're going down by 4 every time. So if I go down by 4, that would be 14. Go down by 4 more, that would be 10. Let's find 30 and 10. Right there. Oh, yeah, I think that works. And let's go down 4 more. So that would be 6, 36 and 6, 42 and 2. So we can use the line, even though the line isn't necessarily valid, because every single point in the line is not a solution to this problem, because every single point in the line would include fraction and decimal values of tables, and we don't really want to have fraction and decimal values of tables. So, but we can use the line to find the solutions that are valid, those whole numbers of small and large tables. And so there is another way that we could have done that. Using the x-intercept and y-intercept to line them up, draw that line very accurately to find those points on the line. And if you're not sure if they work, take any of these x, y values, plug those into the equation. 4 times 24 plus 14, 6 times 14, 6 times 14. And that should equal 180. And I'll let you do the math on that so that we can end this video. Excellent. So there is our lesson on equations with two variables.